Hi, my name is Kevin Hooter. This is my senior design project presentation. I was the team leader. Our project is energy transfer and sustainable housing. Today we'll be covering many aspects of this project. We'll start with background, design objectives, move into testing site prototype flaws, data acquisition methods, calculations, analysis, and budget. Thermal resistance is the ability of a material to resist heat. There are three types of heat transfer: conduction, convection, and radiation. There's a branch of science called building physics that studies this phenomenon. The R value is an easy way to characterize thermal resistance. For example, if a homeowner were to walk into a Home Depot and compare installations, he or she would be comparing the relative R values. So how is R value measured? In industry, there are two prominent methods: center of cavity, which only measures the thickest point of insulation, and clear wall, which only accounts for the insulation and necessary framing members, not corners or intersections with the floor or roof. However, these values are determined using advanced equipment, such as this apparatus, in a laboratory setting, which leads into the thesis of the project. The objectives of this design project is to design a data acquisition method for determining the R value of a residential wall post-installation. Also, to create an accessible program for the use of homeowners in order to determine the insulation capabilities of their own wall composite. To test our data acquisition system, we use the Showcase Home La House. It's an extension of the LSU Ag Center. It showcases to public visitors the most efficient methods and materials to construct a home in South Louisiana. The house itself is comprised of 4 different wings, each with unique building materials. The 4 building materials used in the La House are SIPS, which is Structural Insulated Panel System, ICF, which is Insulated Concrete Forms, Advanced 2x6 Construction, and Standard 2x4 Construction. This blueprint shows the layout of the house. The red dots on the figure indicate where the thermal resistant measurements of our DAC system were taken, along the south wall. From left to right, we have the garage, which is comprised of insulated concrete forms. The blue section represents the kitchen, which is construction using SIPs. Next, the orange section shows the living room, which is built of a standard 2x4 framing. Finally, the west wing is made of an advanced 2x6 framing. Some of the prototype flaws from last semester include improper calibration of instruments. Each thermocouple we used this semester was properly calibrated prior to testing. We also used a different insulating gel, because the silicone-based gel from last semester acted as a heat sink. This caused the temperature readings to be way too high and threw off our calculations. Our advised testing method consists of 3 major components for measuring thermal resistance. Type T thermocouples acquire temperature readings from interior and exterior surfaces. These sensors can be seen connected to the USB-TC in image 1. Also in image 1 is the heat flux sensor, which is connected to the USB 1208FS. Both devices are connected to a laptop computer and are simultaneously interacting with LabVIEW. Image 2 shows a thermocouple on the outer wall of the house with the newly designed PDMS gel. To get proper temperature readings of the inner and outer walls, we needed a gel that would isolate ambient influences. We designed a PDMS gel to do so. PDMS stands for dimethylpolysiloxane. A ratio of 7.5 to 1 PDMS to curing agent was used in creating the gel. We purchased a heat flux sensor that would be able to interact with available data acquisition devices. The way that the device works is by measuring the voltage with the USB 1208FS. This value is then divided by the sensitivity specific value, which is dependent on calibration temperature. The heat flux can be determined by dividing the measured voltage by this value. This slide details how the sensitivity value is calculated. The LabVIEW program we designed takes into account all of the following variables: sensitivity at calibration temperature, linear correction factor, calibration temperature, and mean temperature sensory level. This is the final design of our LabVIEW program. This is the front panel, which is what the user would interact with. On the left side are the user inputs. The user first selects a wall structure with the arrow indicators. We currently have visual diagrams of the 4 La House building system embedded into the program as CAD drawings, with the layers of each composite labeled. Other inputs required by the user are the channel selections, units, and specific sensor values for the temperature and voltage devices. The user then clicks Run in LabVIEW, and the following outputs are given: heat flux, industry R value, measured R value, thermometer indicators of the inner and outer walls, and finally the system percentage. This value shows how much over or under the R value is from its industry counterpart. This is the block diagram of the LabVIEW program. This is how the program receives data from the selected DAC channels and how it calculates the necessary values. Our results compare 3 different sets of R values for the 4 building systems. The literature thermal resistance is the value used in industry. This is the value you would find at a Home Depot. The theoretical value was calculated by dividing the length sum of each layer within the composite by its respective thermal conductivity. And finally, the measured thermal resistance value was acquired using the data acquisition system we designed. Surprisingly, 3 of the 4 building systems were close to its respective industry denoted value, within 10%. The only outlier was the advanced framing section. Because our DAC system was designed as an on-site center of cavity method, we believe that the thickest point of insulation was not properly measured. This error was due to the layout of the master bedroom of the house. A cost analysis was done to stress to potential homeowners how much money could be saved when investing in an insulation. Calculations were done using constant conditions such as electricity costs and wall area. This graph is a visual representation of the previous table. As you can see, while the better wall systems cost more initially, they can potentially save you thousands of dollars in the long run. The budget for this project was $1,900. Fortunately, we were granted access to most of our equipment thanks to the Biological and Agricultural Engineering Department at LSU. Our only major purchase was the heat flux sensor. We spent only about $400 of our budget. We want to conclude by acknowledging the following people within our department: our advisor, Dr. Constant, Ms. Anna Dugas, Dr. Reichel at LaHouse, and Nick Totero. We will now be taking any questions from the panel. Thank you for your time.